This is Lecture 1 of CIVE 360, Mechanics of Solids. And my suggestion as you watch these lectures is to go ahead and recopy the notes. I think that's the number one task that you have before you. I think it's very helpful if you can go ahead and do it. You'll learn something by listening and writing, so just as if you were in a class with me. I think it's extremely constructive if you can go ahead and do that. So I would, again, just basically take notes. It may seem a little bit of a waste, but I assure you it's not. I think you pick up a lot just writing down what we talk about and helping you process that. And you can, just by replicating what I write, it is a helpful learning exercise. So I do have that as a recommendation as we work our way through this class. I want to start off by basically deconstructing the title of this class and mentioning why it's called what it is. Let's break down these words. Mechanics, remember, is a word that basically means response to force. And most of you have already, well, certainly all of you have already had one of the basic mechanics classes, and that is statics. So the first basic so-called mechanics class, again, statics, and that's where we have a system that is in equilibrium. It's not moving, so we effectively have that the sum of the forces is going to be equal to 0. So the class statics really looks at the relationship between forces and moments and torques in various solids. So it all really has to deal with that. How, if I apply one force over at this location, what does that do to the forces at the rest of the locations within that solid? The second class that you do not have to have as a prerequisite for this class is dynamics. And in that case, we have that the sum of the forces is equal to time rate of change of the momentum, but I'm just going to write it as ma. And then we also have that the sum of the moments is equal to I alpha. And that is a relationship then between the forces acting on a particle or a rigid body and the resulting motion. In this class, though, we've got this word, so mechanics of solids, and we're not going to take much time to describe what we mean by a solid, but it is typically we could categorize as basically everything that we're looking at in our room. So if I'm in the cafeteria, then it's the response of a table as I set my tray down on it. If I'm on a construction site, then I've got a 2x4 that's braced up against a wall, and so on. So solids in the context of what we're going to be talking about are some of these entities that we're really just used to dealing with on a day-to-day basis. And don't be a wise guy and say, well, what about my cup of coffee? Of course, we're not talking about something like that. We're looking at a commonly construed solid. Now, something like a piece of clothing, that's going to be a little bit more complicated. That would be a solid in one sense. That's actually what's known as a low-density fibrous composite, and it's got fibers, binder, and air. We're really talking more about when we say solids, things like metals, plastics, and in some contexts, wood, and so on. Those sorts of items is what we're commonly going to be using as we go through our class. So when we say mechanics of solids, then we want the response to force on these things that we typically see as we look around us in our day-to-day experience. And now, though, rather than the case of statics, where we're only looking at the relationship between forces, what we are going to see then is that as the force is applied, the solid deforms. So let's write that up. So as force is applied, then something happens, and we're going to say that the solid deforms. Oops. So that solid deforms. And what we're going to do next is write a little bit of hierarchy that we're going to follow as we work our way through the class. So I'm going to write the following. I'm going to say F is right there. And then I'm going to label that down here, and that's something that we're going to call force. And what happens then is that force is applied, the structure deforms. We're going to use the variable U. to denote that. And sometimes we use the word deformation, sometimes we use displacement. They're not quite the same thing, but in this class, most of the time, there's no rigid body movement of our solid, and so that means that the displacement is the deformation. So we'll, a lot of times, go ahead and shorten this, and we'll just say it is going to displace. So I'll say the displacement. So as we load our solid, then there's a displacement or deformation. And then, once that happens, then there is going to be a point-wise measure that we're going to be spending a lot of time talking about during the course of this class. And that has a symbol that we're going to write as the Greek letter epsilon. And that is what is known as strain. And that is a measure of deformation. It's related to the displacement. If there is a strain in a solid, then there is a partner value of something that is called stress. And we're going to use a symbol sigma to denote that. And I'm going to call that as stress. And there is a relationship between stress and strain. Then the stress has a direct relationship to the applied force, and that is in fact what balances the applied load on our particular system. So this diagram we are going to write over and over and over and over again in our class. So I would say that that is a great sticky note. Because, and by sticky note I mean, you know, a piece of 3M sticky note that you write that little table up and stick it somewhere so that you can look at it every day. Because if you can make that relationship second nature, and you can say, okay, as I have a solid, I've got a popsicle stick, and I do something with it, and then it deforms, and it's linked to strain, then it's linked to stress. It's really going to help you make the link between a lot of the variables that we're going to be introducing in this class. So I would tell you, I'm just going to use a shorthand, I'm going to say memorize that. And again, that's shorthand for commit that diagram to memory, and it's going to be very, very helpful to you as we work our way through this class. So, mechanics of solids, that's what we're talking about. We're talking about the relationship then between the force acting on it and then that displacement that leads to these other variables that we've got. Now, before we move on, I want to contrast this. When I first actually came to CSU over 30 years ago, there was another name for this class. So, other names for the same sort of material taught at different universities. When I came, and when I took it, I was an undergrad at CSU a long time ago, and it was called Mechanics of Materials. That's the word, and that's a fine name. Unfortunately, I think that when you use something like materials, if you talk to, for example, our associates in mechanical engineering, and they talk about material science, a lot of times that can be a matter of scale, and there can be other meanings associated with it. And I'm not a fan of that particular phrasing. But it is one that is used quite commonly. And actually, when I came, I taught this class a number of times, and I thought, you know what, I don't really like this word, so I put in a proposal to change it to solids. And that's why it has the name that it does today. So it's basically my fault. Mechanics of materials or solids. There are other names, and one of them is called strength. Wow, sorry about this. Strength of materials. Not strength of solids, strength of materials. So it's that word. Well, you're going to find, and we're going to repeat this in just a few minutes, strength has a very specific meaning, and it has a association that we are going to make, and it's restrictive. So when we say strength of materials, it's kind of limiting, because when we say mechanics, it means that there's a response to force, and the mechanics then, we are really interested in these two things. We want to know that guy, and we want to know this, for reasons that we'll be explaining shortly. When we say strength of materials, it was really only focused on stress. So strength of materials, in my opinion, is not a great title either. Then some people at some universities also call this mechanics. I'm getting tired of writing this, so I'm going to abbreviate it. Mechanics of deformable bodies. So they've got our word, response to force, but then instead of solids, they use that. So deformable body, well, that's too many letters for me. Deformable body. That's 6 syllables versus solids. So I vastly prefer that particular title. So all of these are used at various universities and institutions across the United States, but we like mechanics of solids. So that's the one that we're sticking with. But I did want to point that out as a difference that you'll see between a lot of these. So what are we trying to do in this class? Our goals. And they kind of fit in with the title of the class. And what we're going to do is we're going to take some solid. It can be anything that we would like. And we really want to answer 2 questions as a solid mechanicist. And we're all in this together, so that's what we're going to call ourselves. We want to take that solid and figure out 2 things. The first is, will it fail? Is it going to break? Is it going to bend? Is it going to shatter? Is it going to be able to hold the load without just falling apart? So will it fail? And that particular quantity is actually related to stress. So that's what we care about there. And that is actually the question of strength. So we do care about that. How strong is the material? How much stress can it take before it fails? But there's another quantity that we care about, and that is how much does it move? Question mark. How much does it move? And that is related to the variable u. So those 2 entities are what we care about for any solid, and that is what we're going to spend a huge amount of time trying to figure out. And that is also a great time then to end the first part, and I'm going to call this part A of this particular lecture.